Hello, we have an introduction to Gibbs paradox, which is related to the extensive nature of entropy, and we have seen that as per the semi-classical expression for entropy that we have derived, the entropy of a system is obtained as different from the entropy of its parts, or the semi-classical expression for entropy was not able to support the extensive feature of entropy. Means we smell some trouble. Now we will make the Gibbs paradox a bit more elaborate by considering the mixing of two gases and calculating the change in entropy during the process. So let's consider two ideal gases. Consider two ideal gases one and two getting mixed. So let's say N1 V1 be the number of particles and volume of the first sample, and N2 V2 be the number of particles and volume available for the second sample. And let us say that both of them be at the same temperature T. So the temperature of both the samples is taken to be same. So this is the first sample in the first container and second sample in the second container. So let's assume that some inert gases like helium and argon are getting mixed. So the situation is shown in the diagram below. So there are two gases, say helium is taken here and say argon or neon is taken on the other side, which are almost behaving like ideal gases. Now we will calculate what is the entropy of the system 1 before mixing, which we will call as S1, and entropy of second system before mixing, that is what, S2. And after opening this particular valve, the two gases will get, of course, mixed up, and we'll calculate what is the total entropy after mixing, and we'll check what is the change in entropy during the process, if any. So let's write the semi-classical expression for entropy. We have the semi-classical expression for entropy. S is equal to Nk, I'm rewriting that expression we have derived already, Nk V by H cubed into 4 pi Me. By the time I think you are quite familiar with this equation, divided by 3n whole raised to 3 by 2, then plus 3 by 2 Nk. So this is our semi-classical expression for entropy. Let me begin with this equation. Let me make a small substitution for the energy in this expression, because we have taken the macro state variables to be N1 V1, and instead of energy E1 we have taken what, the temperature T. So let me rearrange this expression in terms of temperature. So substituting E is equal to, for ideal gas you know that the internal energy is purely kinetic and it is related to the absolute temperature as 3 by 2 nkt. So I can replace the energy with the temperature here. So with substituting E equal to 3 by 2 nkt, the initial entropy of sample 1, initial entropy of the sample 1, let me call it as S1, initial entropy of sample 1, that is S1. You can see how to denote S1 for the first sample. S1 will be equal to N1. We have to make suitable modification in equation number 1. So you know, for first subsystem, for the first system, N is N1. So N1 K is the Boltzmann constant, log. We have to make suitable changes wherever necessary. V is V1. For the first sample, available volume is V1. V1 need not be equal to V2. Okay, they can be separate. V1 divided by H cubed, making suitable changes in bracket, let me write 4 pi. So the first gas sample will be having atoms of certain mass. So m is the mass of that atom or molecule. So we are taking it as monoatomic, being a classical ideal gas. So 4 pi m1 divided by 3n1 into, for energy we are substituting as 3 by 2 nkt. So what I have to do, I have to just substitute as 3 by 2 nkt, n1 k into t. Temperature is the same everywhere, so let's keep it at t raised to 3 by 2, okay, plus 3 by 2 n1 k. So let's make some possible cancellation. This 3 and 3 getting cancelled, n1 and n1 getting cancelled, and 2 and this 4 getting it becomes 2 there. So what is this equation becoming? So this equation can be written now as, I'm simplifying it as n1k log, okay. So let me split up this equation. So I'm taking n1k log v1 as separate, n1k log v1 as separate, plus what is remaining. So here it is raised to log raised to 3 by 2, right? So it will be equal to, again, that 3 by 2, I'm writing log a raised to b is equal to b log a. So I'm taking this 3 by 2 as 3 by 2 n1k log, what is remaining there? So what will be remaining is 2, v1 is taken outside, so it's 2 pi m1 kt, 2 pi m1 kt divided by, see what I'm doing is that I'm taking here h cube is outside the bracket, let me take this h cube inside. So since there is already 3 by 2 here, it becomes what? H square. So divided by h square, we do it because it will help us later. Then plus, what is the third term? It's as such, that is 3 by 2 n1 k, right? So which I am once again making a small rearrangement, that is first term I'm retaining as such n1k log v1. You will understand why we have done this v1 separate, because we have seen that yesterday the problem with the extensive nature was due to some 2v that is appearing in the first term of equation number 1, okay, where the 2 appearing with the energy and 2 appearing with the n in all those equations were getting balanced, but there was a 2v. So I'm separating out that particular term here. That is only why we are doing it like this, the motivation behind separating out the first term. So plus 3 by 2, you can see now 3 by 2 n1 k is common in second and third term. So I'll write 3 by 2 n1 k into, so this term I'm writing as 1 plus what is remaining, log of that quantity, that is 2 pi m1 kt divided by h square. So let me say this is my second equation. So that is my equation number 2. Same manner we can rewrite the entropy for the second sample, sample 2. Same manner I'm writing similarly for sample 2, S2 is equal to, in the same lines I'm writing N2, the number of particles is there, N2k log, the volume available for sample 2 is V2 plus 3 by 2 N2k within bracket 1 plus log 2 pi, the mass of that atom will be different, so I'm writing 2 pi M2 k into T. T is the same for both, divided by what? So log of this entire thing, of course, divided by h square. So let me say this is my third equation. Now you know that after mixing, so we found entropies before mixing. Now we are going to find out after mixing. After mixing, each gas molecule can now occupy a total volume V. Each gas molecule, you know, because we are assuming that gas molecules are point sized or zero sized, can occupy, each gas molecule can occupy total volume V, which is equal to, of course, V1 plus V2. Therefore, total entropy of the mixture. Therefore, total entropy of the mixture. Total entropy of the mixture can be written as S total. We call it as S total. S total is equal to, what will be that one? Just you have to sum up that equation for S1 and S2 with the volume instead of the volume V1 and V2. Now the entire volume V is available for both the molecules. So I have to replace V1 and V2 with the total volume V, and then I can add up S1 and S2. So what will be the thing? First term will be N1 K log, it was V1 there. Now after mixing, the entire volume V is available, so I'll be writing V instead of V1, plus similarly you'll be getting a term N2 K log V from the second entropy S2, plus what do you think? There will be common terms 3 by 2 N1 K into 1 plus, this is from S1, equation number 2 I am writing, log of 2 pi M1 KT divided by H square, that is from S1. Similarly, you will be getting a term from S2 also, this term from S2, that is nothing but 3 by 2 N2 KT into N2 K into 1 plus the same thing I'm writing, log 2 pi M2 KT divided by H square bracket. So that is the thing. Now let's rearrange this one. You can see that here it is K log V is repeating in the first two terms. So I can take it outside and I can write it as N1 plus N2, that is common term. Okay, common term is K log V. I'm writing into K log V, and in place of V I can write V1 plus V2. V is nothing but V1 plus V2 plus the other two terms as such. So I'm writing this term as A and this term as B. So I'm writing, okay, to save time, A plus B. So that will be my, say, fourth equation. So this is the total entropy after mixing, and we are interested in calculating the change in entropy. Therefore, entropy of mixing, that is entropy generated during mixing. Entropy of mixing, that's the meaning of entropy of mixing. Entropy of mixing or change in entropy. You know, the change in entropy, if any, means it should be due to the entropy generated during what? The process of mixing. Or change in entropy, let me call it as delta S. Delta S. So what should be delta S equal to? That should be equal to final entropy of the system, that is S total, minus the initial entropy, initial total entropy, that is sum of S1 and S2, which will be equal to, I can directly write that equation. What will happen, you can understand. See, the final entropy is having N1 plus N2 K log V1 plus V2 as one term. Okay, and the terms A and B, what we have written here, was present in equation 2 and 3 also. Means in S1 and S2 also A and B is present, and S total also the same A and B are present. So the A and B will be getting cancelled in both the things. So what remains is only N1 plus N2. From equation number 4 I am writing this one, K log V1 plus V2 will be there. Okay, minus from the first term given by equation number 2, from S1 there will be N1 K log V1, and from the second entropy S2 will be getting similarly this term N2K. So it will be N2K log V2, which we can modify a bit and write, since you can see that the term N1K can be taken. So it will be equal to N1K. So on opening this bracket, you will be getting N1K log V1 plus V2 minus N1K log V1. So I can write this one as N1K log. I'm taking log A minus log B equal to log A by B, which can be written as V1 plus V2 divided by V1. So I have used this term and the first of this particular term, then plus second one, there will be N2K log V1 plus V2 minus N2K log V2. That will be equal to N2K log v1 plus v2 divided by v2. That's a modification, that's all. So let me call this one as some equation number 5. So look at this expression. Delta S is equal to n1k log v1 plus v2 by v1 plus n2k log v1 plus v2 by v2. Means it's not 0. Okay, it's not 0. Because you can understand that these two terms on the right side will not be getting cancelled out. They need not get cancelled out. Because n1, n2, v1, v2, all those things are what different. So they need not get cancelled out. So clearly we can say that delta S, as per equation number 5, clearly delta S is greater than 0 or positive as expected. Why do we say that we expected this result? Because we know mixing of two dissimilar gases is an irreversible process. Since mixing of two dissimilar gases, you know, they are completely distinguishable, right? You know that you cannot get back by reinserting the gap. You cannot get back see the entire helium on one side and the other neon on other side. You cannot reverse the process. So the mixing of two dissimilar gases, you cannot recreate the initial situation or initial condition, is an irreversible process. And we know basically from the second law of thermodynamics that during every irreversible process, thermodynamic process, the entropy will be getting increased. Okay, therefore we know that delta S should be increased. So that is why we have taken this is as expected. Now let me do one more thing. So there is no any problem with entropy of mixing. There is no any paradoxical situation when we consider the mixing of two dissimilar gases like helium and neon. Okay, so let me take the same equation number 5 a bit more forward. So let me take a special case. I'm considering a special case, may be useful later. So if the particle densities, we know n1 v1, n2 v2, all those are different for the two samples. But let us assume that the two samples have got same particle density before and after mixing. If particle densities remain the same, this is a special case or assumption, remain the same. It can happen so, remain the same before and after mixing. So if the particle density, what does mean particle density? That is n, number of particles, okay, per unit volume is particle density, that is n. Let's say that the particle density is n, so that is n1 by v1, that is the particle density of the first sample, and let's assume that this is equal to n2 by v2, the particle density of the second sample. Even though n1 v1 and n2 v2 are different, let's assume that their particle densities are what? The equal. So by using the law of using the laws of ratio and proportion, I can write therefore this ratio will be equal to n1 plus n2 divided by v1 plus v2, which you can, I think you know it, or you can just cross check it by taking any two numbers and the ratios. Okay, so let me assume this one. So let me say that this is my equation number 6. So assuming this, I'm rewriting equation number 5. So we can rewrite equation number 5 now in terms of n1 and n2 in place of v1 and v2. So have a look at equation number 5. So our equation number 5 is delta S is equal to n1k log v1 plus v2 by v1, v1 plus v2 by v1 plus n2k log v1 plus v2 by v2. That is our expression. Now what we will be doing, we will be substituting for v1 and v2 in terms of small n. Okay, so let me write it here. Hope you can follow that. So therefore equation 5 will become delta S, and you know it's a special case. So I'm writing it as delta S some star. It's a special case in the event of this particular condition. Delta S star. Okay, so that is equal to n1k log then v1 plus v2 by v1 into r. So v1 I am writing as v1 can be written as this. You rearrange this one n to here, so I'm writing it this n1 by small n, right? Plus v2 similarly can be written as what? n2 divided by the same small n. So therefore divided by V1 it was, so it will be once again N1 by En. Okay, then plus N, similarly the second time is also rewritten N2k log. Okay, again it was V1 plus V2, so it will be N1 by En plus N2 by En whole divided by V2 it was, so it should be equal to N2 by En. All right, so you can just this N here will be getting mutually cancelled away, and finally I can rewrite the same expression as what? N1k log N1 plus N2 divided by N1 plus N2k log N1 plus N2 divided by N2. So let me say that this is equation number 7. Okay, and you can see that since this N1 plus N2 is greater than N1, since same argument, so in whatever way, since N1 plus N2 is greater than N1, you can say that log of that quantity, log of N1 plus N2 by N2, that will be log of a number greater than 1, that will be what? Greater than 0. So N1 is positive, and this log of this number also will be what? Positive. Similarly, log of this one also will be what? Positive. Okay, so all these terms are positive, so delta S must be what? Positive. So delta S is once again positive, even if you take this condition. Remember, I think you already have understood it. I just forgot to mention that one. Why do we say that this delta S is positive? Why do we say that delta S is positive from equation number 5? That is because you can see here the terms in the delta S equation for 5 is N1k. N1 is positive, k is a positive constant, so whether or not this quantity will be positive will be depending on log of V1 plus V2 by V1. You know that V1 plus V2 is anyway greater than V1. So this is a number, the log of a number greater than 1. And you know that log of 1 is equal to 0. Log of 1 equal to 0. Log of 10 is equal to 1. Means log of a number between 1 and 10 will be lying between 0 and 1. Okay, and the log of numbers which is less than 1 will be negative. But you know that log of V1 plus V2 by V1 will be a number that is what? Greater than what? Of course, 1, so greater than 0, which is what? Positive. So the same argument here, log of V1 plus V2 by V2 also will be what? A positive number. So both the terms in equation number 5 are positive, and that is the reason why I just told you that delta is positive. That is how we have concluded that delta is positive from equation number 5. The same result, delta is positive, we are obtaining even if we express delta S in terms of the number of particles. Okay, so delta S is positive in both the way. Hence, there is no trouble, right, in the mixing of gas. There is no any contradiction with the what you call the predictions of thermodynamics. Okay, there is entropy gets increased during mixing. Now, let me go to a different case. What's the different case? So far, we discussed the mixing of two samples of dissimilar gases, helium and say neon, or helium and argon, or argon and neon. Now let us consider the mixing of two samples of the same gas. Two samples of the same gas. For example, I am mixing helium sample 1 with the helium sample 2. Maybe here the first sample is having N1. Okay, the volume may be V1 and the temperature is T. Here the second sample of helium is having maybe different number of particles there, N2 to begin with. Let the volume be V2 and the temperature is what? Once again T. Now let us see what will happen if you open this particular valve to allow the two gas molecules, two samples to mix up with. Okay, so the same manner we will calculate the change in entropy. Now I think we can skip many of the equations in between, and we can directly write down the final result. So with slight modifications. Now consider the mixing. Consider the mixing of two samples of the same gas. Two samples of the same gas. So what change should be brought in here? That is what difference will be there? Earlier we have been taking the atomic mass as M1 and M2 separately, because for helium it will be M1, maybe for argon it is what, M2. But here, since the two samples are the same, let's take M1 equal to M2 and let's take it as equal to Em. So what will happen is that the total entropy of the mixture, therefore the total entropy of the mixture as usual, I'm not writing S1 and S2, you know, okay, that is S total, that will be equal to same expression, just you can compare with the previous expression, N1 plus N2 K log, there is no difference going to happen here, V1 plus V2, because the M terms are getting cancelled away, plus, okay, so 3 by 2 N1 plus N2 K, I can combine the second and third term in S total. Okay, so let me just take you back. So in the S total here, you can see in the S total we had this term combined to give you N1 plus N2 K log V1 plus V2. We are written aside. We had terms A and B, which was this term and this term. And why did we keep it as what? Just separate, because here there was M1, here there is what? M2. Now in our present case, M1 and M2 are same, all other terms are same, so the entire bracket here is what? The same in the two terms. So I can take those quantities in the bracket as common, and there only one thing will be different, that is N1 and N2 will be different, so they will be taken inside a separate bracket. So that is what I'm writing just now. So that is 3 by 2 N1 plus N2, okay, into K log, right? So into I can write 1 plus log 2 pi m kt divided by x square. Same things what we have written earlier. So let me say that this is some equation number 8. Okay, again you calculate, so you got see the total entropy. So again calculating the change in entropy. So what will be this one? That is delta S. So what will be delta S equal to? You can see that delta S will be equal to, you have to take S total minus S1 plus S2, which we haven't written. But you will see that in this case also, this term will be getting cancelled away with the terms appearing in S1 and S2. Okay, and what will remain here? What will remain here is same as previous case, that is N1K log, just please check it, V1 plus V2, we have done it earlier, divided by V1 plus N2K log V1 plus V2 divided by V2. We say this is equation number 9, and you can just check it back. This was the same result that we obtained for the delta S in the case of mixing of two dissimilar gases. See, this is the same equation, N1K log, equation number 5, which is same as equation number 5. There is no difference in the equation, which is same as same as equation 5 for mixing of two dissimilar gases. And therefore, by the same arguments that we have taken before, this case also delta S is what? Positive, means entropy increases. Here comes the problem. We know mixing of two samples of the same gases under isothermal conditions, because we have taken T1 equal to T2. Mixing of two samples of the same gas under isothermal condition is a reversible process. I repeat, mixing of two samples of the same gas under isothermal condition is thermodynamically a reversible process. Why it is a reversible process? Because you can see that, see, if you permit this thing to just get open up, right? And since the volume is V1 here, right? The temperature is the same here. V2 is the same here. Temperature is to be maintained as same here. You can see that by reinserting this particular closing cap, we will be able to just get the same system 1 and system 2. System 1 and system 2 will be obtained back by reinserting the partition wall, because the gases are one and the same. Okay, it's just like, is it not? It's just like you have got, you can think in the reverse, that will be easier. Like you have got a bigger system, right? Okay, and you know this is an extensive system. Suppose you put back the partition here, which was earlier there. Then you can see that the same volume V1, the same volume V2. The number of particles here will be N1, number of particles will be equal to N2, and the temperature is what maintained equal. So you will be getting, whether you remove this one, okay, or you just reinsert this one, since the gases are the same on both the sides, you will be able to get back the initial situation reversibly. Okay, so this is actually a reversible process. Means in a reversible process, you know, the delta S should be equal to what? 0. Delta S should be equal to 0. So for the mixing, we expect thermodynamically that for the mixing of for similar or same gases, delta being a reversible process, delta S must be equal to 0. But we get what? Delta is positive, as in the case of two dissimilar samples. Means there exists a discrepancy. Therefore, there exists a discrepancy, vairudhyam, okay, or paradox, when we consider the mixing of two samples of the same gas. Or this discrepancy is what is better known as what, or it is supporting what is known as what? The Gibbs paradox, or the what I call as the entropy of mixing. That we get a non-zero entropy change for a process which is what? Thermodynamically reversible, which is, of course, we cannot agree with that one, because thermodynamics is an established fact. All the laws of thermodynamics are fundamental laws of nature, which has been experimentally verified. Okay, and our statistical mechanical predictions using the semi-classical expression for entropy gives a negative result for a verified fact, which is of course a paradox. Means our conclusion is that, where did we begin all this discussion with? We began with the semi-classical expression for entropy. So there is something wrong, there is something fishy, something wrong with the semi-classical expression for, this should be our normal conclusion for entropy. And I don't know whether you remember, I had told you while discussing classical ideal gas that even though we could obtain the equation of state and the thermodynamics of a classical ideal gas by starting with what? The entropy expression, I told that we cannot celebrate completely. The reason is that even though we got those thermodynamical expressions derived correctly for a system like classical ideal gas, it doesn't mean that that equation is correct forever. Even with the minute errors in an expression, sometimes you may get some results as correct. So this is a case where that expression is found to be insufficient to explain the entropy of mixing. Hence, we have to recheck the derivation of our expression, and we have to check where we have gone wrong, what mistake we have committed in deriving the semi-classical expression for entropy. And if we are able to correct it, then that is known as resolution of the paradox. So we will just discuss about how to overcome the problem that is that has occurred in the semi-classical expression for entropy, and thereby how to resolve the Gibbs paradox. So the resolution of the Gibbs paradox will be discussed as a separate session. You can read on while, and we will come back with the resolution session. Thank you.